So here's your first question on this one. Calculate the E for this half reaction. And I'm giving you some values of delta G. Okay? So hopefully you can kind of see where this one's going. I'm going to give you a couple of minutes to work on this, because we can't take a lot of time on each of these, and then we'll talk about it together. Okay? Okay. So let's go ahead and talk about this one. So first thing on this one that you should probably notice is that we're going to have to use, because we're relating delta G to E, we're going to have to use the equation delta G equals negative NF E0, right? Okay, but before we plug in our delta G for this equation, we actually have to find out what it is, because all we have is some delta G's of formation, okay? So remember, to find the delta G of formation, it's products minus reactants, right? Okay? So, if you take the product, the only product that matters here is the OH minus. Why is that? Okay, the H2 is in its standard state, okay? So that is going to be 0. In case you're worried about this, electrons also have a delta G of 0, okay? Delta G of formation of 0. So, because a book told me. So negative 157 kilojoules per mole times 2, right? Because we have a coefficient 2 in front of the OH minus, so watch that. Minus the reactants, which is negative 237, again kilojoules per mole, times 2 for the H2O, and that should give us our number, okay? Should give you 160 for your delta G. Okay. This is the one place where you're going to get messed up on this problem if you're not careful. That's 160 kilojoules. Remember, on the quiz, we just talked about the fact that F here is measured in joules, right? Faraday's constant. So it's got to be 160,000 joules if it's going to work in this equation, okay? All right, so then we've got how many moles of electrons being transferred here? 2. So negative 2 times 96,500 times the E0, which is what we're trying to solve. Okay? Alright, so once we figure this out, we're going to end up with an E of negative 0. How many sig figs here? 829. And that's going to be volts. Okay. Now, let's think about that for a second. Does that make sense? What was our delta G? It was positive, which means this reaction is not spontaneous in the forward direction. Okay. So getting a negative voltage makes sense. That's why these two are actually opposite of one another. Okay. If you get a positive delta G, you should be getting a negative E. If you get a negative delta G, you should be getting a positive E. Okay? So that's how those are related to one another. So again, a good way to check yourself at the end and make sure that you're on the right track with the number that you get. Alright, next. The overall reaction in a lead storage battery is, we were talking about this the other day, so I thought I'd throw this problem in here. A lead battery is lead reacting with lead oxide, which is kind of interesting. So it's all lead. So here's the question. See if you can figure this out. I'll give you a few minutes on this one because this one's going to take a little bit longer. Okay. So let's just go ahead and talk about this one. Again, I like this question because it's applicable. This is actually what's going on in the battery in your car. So you've got this reaction, and they're wanting to know the E when we have these certain concentrations here. So obviously, you know, the standard concentrations doesn't work here. This is much more concentrated than that. Okay, and so what we're trying to figure out here is how does that affect the voltage of this particular reaction. So what we're going to do here is, you know, use the E equals E0 minus 0.0592 over N times the log of Q. Alright? So a lot of these things we can figure out fairly easily. The E here is what we're trying to solve for. They give us the E0, it's 2.04 volts, minus 0.0592 over, okay, this is where you got to be a little careful, okay? It might just, you might think off the top of your head, oh, 2 here, okay? But remember, the best way to figure out how many electrons are being transferred is looking at the oxidation states overall, okay? This lead is a 0, okay, and it's going to a, this is a 2 plus over here, but there are 2 of them, so overall that's going to be a 4 plus, right? Okay, over here this is a 2 plus, I'm sorry, a 4 plus, but it's going to a 2 plus, and there are 2 of them, okay? So there's only one of these. There are 4 electrons being transferred here is what's happening, okay? Does that make sense? I just confused everyone. Yeah, probably so, because it looks like nothing's happening there. This is going from a 4 plus to a 2 plus, but because there's 2 of them, there have to be 2 electrons lost in each of those, okay? 2 electrons gained, sorry, for the reduction. Yep, I'm messing this one all up. Okay, so it's going to be 4. 4 is the correct answer. All right, it's easier to see when you're going from the solid lead to the 2 plus, and since there's 2 of them, then it's going to be 4 total electrons that need to be transferred. Okay, times the log of Q. Now Q here is kind of different, all right, because remember, we don't include solids or liquids in our equilibrium expressions, or in our Q expressions. So actually, this is just going to be 1 over some things that are on the reactant side, okay? And so, really, it's our H plus concentration here squared times our HSO4 concentration squared, okay? And they're saying those concentrations are 4.5 molar each. Hopefully you guys understood that, because the H plus is equal to the HSO4 minus, which is equal to 4.5 molar. We're assuming that first hydrogen on the H2SO4 completely dissociates, because H2SO4 is a strong acid, and then we're assuming that the H plus coming from the HSO4 dissociation is negligible at that point. Okay, so going back to our strong acid stuff. So once we find our Q here, figure this out. So 4.5 squared times 4.5 squared, take 1 over that. Our Q is going to be fairly small here. It's going to be 0.0024 something. Okay. So when we take the log of that, that was not what I wanted to do. The log of that, it is a negative number, which should tell us something about the voltage. It's actually going to get higher at these concentrations. Kind of makes sense. That's probably the kind of concentrations we would want in our battery so that the voltage is higher, okay? So then we divide that by 4, multiply by 0.0592, and then add that. What did I do? I did something wrong. that seems like the least likely solution to what happened here. Okay, log of 0.0024. Let me try this again. Oh, that's what I did. Okay, so I'm getting about 2.07 here. Okay, not a huge jump in voltage. 2.08 for the voltage. Okay. Now, I like this second part of the question here. What did I do? Oh, 4.5 molar. Sorry, so it'd be 2.1. 2.1 volts if we're worrying about the sig figs here. Okay, the second part of this question I like, because you have to figure out here, how is the E related to some other things like reaction spontaneity and that sort of thing, okay? So, remember, delta G is related to E by this equation, right? Delta G is also equal to delta H minus T times delta S, okay? So we can relate these two to one another. Is equal to delta H minus T times delta S, okay? Now, you don't have to use that equation. There's a couple of ways you could think about this. You could think first about how spontaneous this reaction is, and then you could relate that to the voltage, which might be the easier way rather than looking at this equation, okay? But what happens when something has a positive delta S? Thinking about this equation right here, what happens to the overall value of delta G as the temperature decreases, like on a cold day? If the delta S is positive, as the temperature goes down, it would be a larger negative number, correct? Oh, wait, if temperature goes down, yeah. So if temperature goes down, okay, then what that's going to do is decrease our delta G overall. Does that make sense? Am I saying that backwards? Right. So then your delta H, you've got a negative delta H here, minus a okay, yeah, the lower the temperature, the less negative the delta G. Okay, thanks. I was thinking delta G was positive first, but it's not. Okay, this is very spontaneous to begin with. Okay, sorry about that. So the lower the temperature, the less negative the delta G. In other words, the closer we're getting to not being spontaneous, or the less spontaneous it is getting. Does that make sense? Okay, because it's a less negative delta G. So on a cold day, the reaction is less spontaneous than it would be on a warm day. If that's the case, that's going to cause the voltage to go down a little bit, okay? And so that's why on a cold day, your battery will fail more often than on a warm day, okay? Right, it makes a less spontaneous reaction. Okay, here's our last one. I'm going to give you guys a couple of minutes on this one. It's long, and it's all equilibrium based. So, okay, let's talk about this last one here. Oops, let me do that. So I think a couple useful things here that might help you out. First of all, I would write the overall reaction. Okay. I think that's going to make it easier to think about, because if these are all equilibrium type questions, then what we're thinking about here is we're thinking about Q, okay? So basically we've got copper 2 plus going to copper and Ag 1 plus going to Ag. Well, no, we don't have that. We've got to figure out what is going to happen here based on the reduction potentials, okay? Because they're both written as reductions at this point. So you're going to have to use your reduction potential chart, but which one of these is going to be the reduction, in other words, the cathode half reaction? Silver, right? Okay. So the silver we can keep as written, Ag plus plus E minus. Say that again. Right. Right. Yeah, so that's one way to think about it, I guess, is that silver solid is fairly unreactive because it doesn't tend to get oxidized by things. So when you have Ag plus, it wants to get back to solid form as soon as possible. All right, so then we need to flip the way that we wrote the copper equation, because that one's actually going to get oxidized. So you're going to have copper oxidizing to form Cu2 plus 2 electrons. We're going to have to multiply this one by 2. This is a little redundant based on some of the earlier parts of the video, but it's not redundant for you guys because we didn't do it in here. So your overall equation here is going to end up being 2Ag plus copper yields 2Ag solid plus Cu2 plus. Okay, I guess I should have labeled this as solid since I did the other one. Alright, so there's our overall reaction. That's going to help us with our Q. Alright, and so then we just need to be thinking about this equation here. E equals E0 minus 0.0592 over n times the log of q. Okay, and what we really need to think about here is the log of q expression going to give us a positive or a negative, or how is it going to change, and then how is that going to change the overall voltage? Okay, so we've got CuSO4 solid, we're adding that into the copper half cell compartment. Okay, so you add copper CuSO4 into the copper half cell compartment, what's going to happen to it? Most likely it's going to dissociate, right? So what that does, essentially, what we care about here is that it's increasing the concentration of the Cu2+. All right. So let me actually write the expression for Q over here so we can be thinking about this as well. It's going to be Cu2+ over the Ag+ squared. Okay. Not that that really matters too much on this one because we're just thinking conceptually, but the increasing the concentration of the Ag+ is going to have a greater effect than increasing the concentration of the Cu2+. All right, so we are increasing the Cu2+ concentration. What's that going to do to Q? We're going to increase it. What's that going to do to this whole expression here? Going to increase it, right? What's that going to do to our E? It's going to decrease it, right? Does that make sense? Okay, so decrease the cell potential. That's what they're asking us about, or decrease the voltage, okay? All right, next one, the NH3 is added to the copper half cell compartment, and they give you a nice hint here. What that's actually going to do is take some of the copper 2+ out of the solution, okay? So if that happens, what does that do to Q? It's going to decrease it, right? So that does the exact opposite of what we were just talking about. Since it decreases it, that makes this whole expression smaller. Okay, that's going to actually cause our E to increase a little bit from what it was. All right, NaCl is added to the silver half cell, and once again, we're just messing with one of the ions here. So that's going to take the Ag+ out of solution. When it does that, what does that do to Q? It increases Q, so that's going to have the same effect as A, right? It's going to cause the overall potential to decrease. Now we're adding water to both half cell compartments until the volume of the solution is doubled. Okay, this one's a little tricky. It would stay the same if this is a 1-to-1 stoichiometry, right? But what happens, let's say that we've got, 1 molar here, 1 molar here, and then we cut both of those in half. See, it's going to have a different effect on the silver than it has on the copper. Do you see that? Okay. So ultimately, having the concentration affects this more, okay? Which I believe that's going to cause our Q to increase. Is that correct? Am I thinking about that right? Because it's going to decrease this by a greater amount, okay? So if it causes our Q to increase, that's a tricky one, all right? If it causes our Q to increase, then it's going to do the same thing as A and C. It's going to cause our voltage overall to decrease. Okay? And that all comes from that equilibrium expression there, or the Q expression. Now, one thing I did not mention, but I don't think we really even need to practice this. Okay, there's one more equation that's really not on this practice. The log of K equals, oh, now I'm not remembering it. Is it NF? NE over, thank you. Okay, equals NE over 0.0592. Okay, now I don't think we really even need to talk about a problem where you have to do that, because essentially it's just if you have to solve for K and you're given the E, you guys can do that, right? Okay, all you have to do here, all you have to remember on this one, the only hard part is that to get the K by itself, you have to 10 both sides, right? Okay, so just don't forget about that. Alright, I think that's pretty much it. If you watch all the videos for this, you should be very well prepared for this test.